Hello everyone, Sean here from SMD Methods. You're very welcome into this video in which we're going to look at an optimization problem as set out by Steve Chapra in his 8th edition of Numerical Methods for Engineers. Problem 16.40 sets out a challenge to determine an optimal cruise velocity for a jet at a given elevation. Now, although the elevation itself is not provided in the problem, parameters which would represent the height are such as the density of the air in which the jet is traveling at, and indeed the acceleration due to gravity at that elevation, which in itself is embedded within the weight of the jet given in the problem. Now, in the textbook, as you can see, the problem is split out over two columns. So what I've done is I've translated it over into OneNote, where it's still spread out over two columns, in fact three if you take in the graphic. However, what we can do is we can work through the problem in a more structured manner here with the problem defined at the top of the page. So 16.40 states that for a jet in steady level flight, thrust balances drag and lift balances weight. So what we would equate this to is a net zero force acting on the jet, and therefore we should have a constant velocity, no accelerations. So under these conditions, the optimal cruise velocity occurs when the ratio of drag force to velocity is minimized. The drag, given here as C sub D, can be computed as C sub D is equal to C sub D0 plus a ratio of C sub L squared and or over pi multiplied by AR, where C sub DO is the drag coefficient at zero lift, so it's a parameter of the plane. C sub L is the lift coefficient itself, and AR is the aspect ratio, another parameter of the jet itself. So for steady level flight, the lift coefficient itself, which is given as C sub L, this can be computed as 2 times W divided by rho v squared over A, where W is the weight of the jet measured in newtons, rho is the density of the air in which the jet is traveling, V is the velocity of the jet, and A is the wing planform area measured in square meters. The drag force itself, the drag force now can be computed as the weight of the jet multiplied by the ratio of the coefficient of drag to the coefficient of lift. Now, drag is mentioned a couple of places in here. There is one thing I would like to even just clarify on this, even though C subscript D there would always give us coefficient of drag, with no C as a coefficient on this. They say an optimal cruise velocity occurs when the ratio of drag force, so we're specified as drag force here, to velocity. Then over here, we're saying the drag force can be computed. So we know that's drag force, obviously with an F, to velocity is minimized. Now it's just given here the drag. Right? So to me, there is a wee bit of a vagueness in that. Right? The drag C sub D, now clearly it's a drag coefficient because of the C and not a drag force with an F. But to me there, probably wouldn't have done any harm to have written the drag coefficient there can be computed as, because in no place else is it stated that CD is the drag coefficient. Okay, so probably no harm just even take a note of that and resolve in your own minds whether it's needed or not. However, what we're looking for here is a ratio of the force of the drag, F over D, of the drag force, F sub D, to velocity, drag force to velocity. So what we are really looking for is FD divided up by V. Okay, so I'll keep the V there without the normal little arrow I draw over that for the indicate it as a vector. So FD over here, this is going to be equal to this expression we're getting here, which is W by C sub D divided up by C sub L, all divided up by V. So what I'm going to do is I'm just going to put the V over here. So this is what we're looking for here. Okay, so let's get to work on rewriting this, or deriving an expression that gives us F of D, or F sub D, over V with respect to the parameters of the jet and the fluid, the air at the elevation that it's flying in. So instead of just saying C and D and C and L, let's get rid of C and Ds and CLs and let's repopulate that with aspect ratios and planform areas and densities and whatnot. So let's go for it. So what we'll do to do that actually is, let me just take a wee bit in here. For CD, I'm going to plug in this expression here. And that's going to go up into the top. And indeed, then for CL, I'm going to plug in this bottom expression. We'll do it over 2 steps as well, just to keep the maths slightly more navigable, maybe. So we'll do CD. We'll put in CD there first. So let's take it on over here. Probably just do as well as any. So let's start up here and let's go for F over D over V is equal to W over V multiplied by. Now for the CD, I'm going to plug in this expression. CL, I'm just going to keep it CL for now. So what I'm going to do is I'm going to put in a curly brace. I'm going to take in a square brace for this section. And this section is going to be my CD section, which is CDO plus C sub L squared over pi by AR. And that, of course, is divided then up by CL, C sub L. In fact, what I'm going to do, this AR, I'm going to put that into its own bracket. Why? Because the A in that AR, to me, can be very easily confused with a standalone A, which is also part of this this larger expression. And whilst there's an R coming after it, R is a very commonly used nomenclature for various parameters and variables. So AR together in a lot of cases could be A multiplied by R, where this A is thought of as being this A and R some other parameter that we just don't have on this occasion, but could probably be invented. So let's bring it on down to the next line and let's go on. F sub D over V is equal to W over V, and let's try to simplify this by bringing the CL into both terms. So I'll probably revert to a square bracket. Let's go for C sub DO over C sub L. So that's going into the first term. Plus, let's bring it now into the second term. So where we have a numerator and a denominator, and the numerator itself is a fraction of a numerator and denominator. We combine the two denominators. So this will be C sub L squared over C sub L by pi by AR. And indeed, hopefully we can all see a handy cancellation of one of these CLs, or that CL to one of them CLs. Let's rewrite it for the sake of thoroughness and to tidy this up. So F subscript D over V is equal to W over V by C sub D O over C sub L plus C sub L over pi by the aspect ratio of the jet. Round. Now, our next step is let's substitute the CL for the expression given, the coefficient of lift, which is written with respect to the jet's weight, the density of the air, the velocity of the jet, and the planform area of the jet's wings or aero surface, lift surface. So FD over V is going to be equal to W over V by, now I'm going to go back to the curly brace because like they have a few components in this. I'm going to stay with a C, D, O up in the numerator. This is divided now by another ratio, which is in itself written over 2 lines, 2W divided by rho V squared A. That's CL. Plus, let's write it again, so I have another CL here. oh, not CDO, apologies. I was just looking, because I was writing again, I was looking at the term to the left. 2W divided up by rho V squared A divided up by pi by AR, which is just the denominator here taken through. Okay, let's tidy this up. So FD over V is equal to W over V. I can revert this back to square bracket now. So what I'm going to do here, when I have a numerator divided by another fraction, what I'll do is I'll take the denominator of the denominator and flip it up onto the numerator. Now, which goes to C D O by rho V squared A divided up by 2W plus, and then here again I have a fraction divided up by another another denominator, so I just, like I did up here, combine the two denominators. So here I'll have a 2W divided up by let's go with the rho part first, rho V squared A by pi AR. Now I can now multiply in the W and the V and see, can we get some further simplifications, which I'll be confident we should be able to. So W and the V going in, so obviously I can see I can cancel it, this W and that W, that V with one of them V's, but just to keep this video or this kind of work in this process, these steps, as thorough as possible, so keep it for everybody. Let's just do it out step by step. It's a wee bit longer, hopefully not so much more painful, but it at least doesn't exclude anybody. Rho V squared A by W, so as I did it, I just done my W onto the top. This is still working on my first term, divided up by 2W and then the V comes in on the denominator. Second term plus, this W goes onto the top, 2W by W, so I'm just going to write it like that. W squared obviously, but we'll deal with that in the next line. And then the V onto the bottom, rho V squared by A by pi by AR by the V onto the bottom. Close that bracket there, I missed that one. Alright, so that's the V has been carried through to here and to there, the W carried through to there and to there. Alright, let's do some further tidying up. So F sub D, drag force divided velocity, is equal to, now I'm going to go to my cancelling out color here. I can take one of them V's off here by dividing that V into it. I can take the W out by cancelling with that W. I'll combine these two W's here. And this V, what I'm going to do is I'm going to scoot that and just do that kind of +1. There's another, so that's rho by V by V by V is going to be V cubed. Let's go for it. So we'll go for C D O plus rho B, I'm left with one V, rho V A divided by 2 plus 2W squared over rho V cubed by A by pi by AR. Let's tidy up this second term here a wee bit more. See if I can centralize it, because I'm going to box this off now at this stage. I'll just keep it more presentable looking. Alright, see if we can get that boxed off. Nice. So there's our expression. So that expression there is the one that we're going to use. That's the general expression to give the optimal cruise velocity of a jet at some given elevation. Obviously, a jet of particular parameters flying in air of this density. All right. And as I said, the acceleration due to gravity at that elevation will be encoded within that W, because that W is measured in newtons in this problem, as opposed to kilograms multiplied by some arbitrary value of gravity. So let's keep that. Now, the objective of this one here is to find a minimum, find an optimum of this. Right, so there's numerous ways of optimization. You can use bracketing methods or open methods. So we could, for instance, look about using a golden search method there to find an optimum. We could look at Newton's method there if we want to go for an open one. Various different methods. Regardless of which one we're going to use MATLAB just to iterate through each search, if you like, each movement to find the optimum, until we bring our residual errors or our iterative errors down below a maximum permitted error. But what I'm going to do, I might use this one here just using Newton's method. So if we're using Newton's method, what we want to do is I want to find the derivatives of this here. I need to find the first and the second derivative of this. Okay, so what we're looking at is f of d, or the force with respect to velocity. So what I want to do is I want to find a, say, what would we call it, like a df dv for this one. All right, so I'm going to create a new parameter here. Instead of calling this f of d over v all the time, I'm just going to call this one here, I'll call it s. All right, speed. Right, obviously I don't want to use another v for velocity, sub c for cruise, and I can't use a c for cruise, so I'm just going to call it s. So I'm going to say s of v is equal to f of d over v. And so that there is effectively s of v there. So if I wanted to go for, let's go for ds dv, right, will give me a d dv of this expression here, which is c do by rho va all over 2 plus 2w squared over rho v cubed by a by pi by ar. All right. So what we can do here is we can use the power rule to differentiate this. ds dv, because we don't have anything conflicting there other than single factors of v. But let's rewrite this so we can use the power rule more effectively. CDO by rho VA, that first term's fine, divided by 2 plus, what I'm going to do is bring up this V cubed up to the numerator, make it a little bit clearer. So let's go for plus 2W squared by V to the power minus 3. So again, when you bring a value, you change a factor its position from a denominator to numerator or numerator to denominator. You can move the variable up or down, or the value up and down, once you change the signage of the exponent. So it was plus 3 on the denominator. When I bring it up to the numerator, it's going to be minus 3. I'm just left with rho by a by pi by ar. All right. So ds dv. So let's go for that. Let's differentiate that. So ds dv is going to be equal to, so now see this is v. That's going to go away. There's just one that differentiates down to 1. So we'll have a c do by rho by a over 2. Now this one here, I'm going to go for a plus, right? And then I have a 2 w squared by differentiating that v. I'm going to bring down to minus 3 by v and then drop that by 1, goes to minus 4, all over rho by a by pi by ar. All right, let's tidy this up. 1 ds dv. It's going to be just keep that out of sight. 1/2 of c do by rho by a. Now the minus 3 by the 2 becomes minus 6. Minus 6 w squared v to the power minus 4 divided up by rho by a by pi by ar. Now, indeed, you can bring that v to the power minus 4 back down to the denominator, make that v to the power 4 in the denominator, if you so choose. But what I'm going to do is I'm going to take another derivative of that to use Newton's method for optimization. But I'll write this one out here as a side. So let's go for ds dv is equal to 1/2 of c do rho a minus 6 w squared over rho v to the 4th by a by pi by ar. It's the exact same thing, but what I wanted to do was just bring the v to the power 4 down. So maybe box this one here off in orange. So, okay, that's the first derivative. Now, second derivative. Alright, so I'm going to go for dv of ds dv, which is going to be equal to dv of, I'm just going to use this one up here, which already has the v variable in the numerator, of 1/2 of c sub do by rho by a minus 6 w squared by v to the power minus 4, all divided up by rho a pi by ar. Okay, so we'll put that. So this is d squared s dv squared is equal to, so there's no v's in this first term, so that first term just goes away. So dealing with my second term, I'm going to have a minus 6 w squared multiplied by a minus 4 when I bring the power down to the front by v to the power minus 5. Let's drop my power by 1. Divide the whole lot up by rho by a by pi by ar. Let's tidy that one up. D squared s dv squared is equal to, yeah, I can do it here. So minus 4 by minus 6 is going to go into 24 w squared v to the power minus 5 all over rho by a by pi by ar. And then I'll do the same as what I did up here, just to bring that negative exponent, get rid of the negative exponent. So I'm going to bring the value to which has a negative exponent over to the other side of the fraction to give myself the positive exponent. So d squared, I'm going to tidy that up, it doesn't look so good. D squared s over dv squared is equal to, very simply now, 24 w squared all over rho. I'm going to keep the v next. I should have had like rho a v. Seems to make more sense. It just seems more mass flow rate-ish. But I'll just keep the same order. Rho v to the power of 5 this time by a by pi by ar. That's it. and put that one there in green. Lovely. Okay, so we have our original expression here, our function, first derivative of the function, and we have a second derivative of the function. So what we can look to employ now is Newton's method for optimization in this case, but indeed, once we have our regular function here, we could even use a bracketed method to determine the optimum value. But let's try Newton's method for it anyway. So what I'm going to do is I'm going to pause the video here. I'm going to go on into MATLAB, start up a new script, and when that's going, we'll come back and we'll write these in and see what we can work out from that. Okay. Apologies, I'm just back here again. What I should have did in all the talk about Newton's method was actually write in what Newton's method, the expression for Newton's method. So what we're going to be looking for here is going to be a new velocity value, okay, out of this this minimized expression. So we'll say for v I plus 1, so my next v value is going to be equal to my current v value, and then some adjustment. Okay, so the adjustment on this one here we're going to be working with is going to be my the first derivative over the second derivative. First derivative of the second derivative, yeah. So it's going to be my first derivative, which will be s. Actually, I'm thinking, yeah, I'll write it like this: s of v over my second derivative s subscript of v. So what I actually should have wrote here is that, by the way, d squared s dv squared is the same thing as s double prime of v, second derivative of s with respect to v. And similarly, this one here as ds dv is the same as s single prime of v. Just keep them together like that. Didn't have to really write that in, but it's just to keep this, a wee bit tidier looking. Instead of writing vi minus ds dv divided by d squared s dv squared. All right, so let's give that a use blue, I think, for writing in something earlier on. Yeah, coefficient. Go purple down here. All right, so this here is that's the expression for Newton's method to optimize, or to find an optima. Really find an optima. So the how do you know if we're finding a minimum or we're finding a maximum? Both optimas. Again, we'll be looking at the second derivative values of the second derivative. All right, so negative values are going to indicate either positive or negative, and the positive or a positive second derivative will indicate a positive or maximum or minimum. We'll talk about that bit there when we get into the next bit, when we actually plot the function in MATLAB, and then we see that it is a minimum. We'll put in a value there, we'll find out the second derivative, and you'll see there how the signage on the derivative relates to whether an optima tends to a maximum or a minimum. Okay, so I'm going to pause this time now. I go into MATLAB, and I'll see you in that environment next. Hey everybody, back again, and we're now in the MATLAB environment. A good bit over 24 hours since I finished the first segment, but sure, that's how these things go. So what we'll do without further delay is I'm going to go on ahead in here, and I'm going to start a new live script. What I'll do is I'll enter in some text, just to give this thing a title here. This is optimization, say, of cruise velocity. This is problem 16.40 from Numerical Methods Engineers Edition 8, Chapra. Control Alt Enter, new section, Alt Enter, and let's put in parameters. Parameters first. Alt enter. So the parameters that we're going to look at are given in the problem here. We have the weight of the jet, 670. Actually, take a note of these. I have to flick through them. So the weight is 670 kilonewton. The area, planform area, is 150 square meters. The aspect ratio is 6.5. Coefficient of drag at zero lift is 0.018, and rho, the air density of that elevation, is 0.413. Of course, that's kilograms per cubic meter. There's no other parameters, and you have pi in there. That's it. That's okay. Let's try it. So the first one is W. W is equal, that's the weight of the plane, is 670,123. And this is going to be the weight of the jet measured in newtons. A is equal to 150, which is the planform area of the jet's lifting surfaces, generally the wings possibly, measured in meters squared. AR is equal to 6.5. This is the aspect ratio of the jet. CDO is 0.018, which is the coefficient of drag at zero lift. And then finally, rho is 0.413, and that's the air density. Air density at cruise elevation, measured of course in kilograms per cubic meter. All right, and that's all the parameters done. Okay. So I'll go down here, Control Alt Enter for a new section. There's the parameter. So what I'm going to do now is start off with cruise velocity, say using Newton's method. So we need to know where to start with. So for Newton's method, we need a initial guess, and the initial guess needs to be fairly close to the optima. Now, if there is only one optima in this, or in this kind of wide range, we don't have to be as critical, but where we might have a sort of a function that looks just indicative of a wave or so, we need to be much more careful on that, because our derivatives might start tracking the wrong minima depending on what the first derivative, what the slope is. It might take us very close to another optima. So we need to know where to start with. So what I'm going to do is I'm going to set up a computational space here. Computational space for function. So just to get the function, have a look at the function, see where the optimum is, so we can pick up an initial guess. Computational space for function. Computational, not space, go for facilities. Just to plot the function plot is going to be the main objective here. Alt Enter. So what we're going to do is we're going to set up a velocity vector, because I need a plot. I'm going to plot my I called it S, I think it was. Yeah, S of V, and I'll plot that against V. So V is going to be my independent variable here. So V is going to be, I'm going to start off, I can start with, well, it's not going to be 0 clearly. I start off with 100, go up in 0.5 increments, and I have no clue where this cruise velocity is. So let's try up to 500 just to see if if our optima is too far one way or the other, we'll adjust that again. And then I'll initialize a variable here for s. S is going to be equal to zeros, one row, and then number of elements in V. So I'll have an S for every V. All right. So what I'll write now, I'm going to try my function. I'll go S function is equal to add. The input is going to be V. V is, yes, absolutely it is. It's a matrix. It's a vector here. But I am not going to do matrix multiplication on this function. I'm going to use a for loop. It's just a way I prefer to run these, is to use for loops. So that's what I'm going to do. So my function, I don't have a copy of my function here just yet, but I will take it. It's there. Let's paste that in, because then I don't have to keep scooting back and forth. So my function is going to be 0.5, which is just the 1/2, by the CDO multiplied by rho multiplied by V multiplied by A. Okay, so again, I'm not doing matrix multiplication, so that's why there's no dot V in that now. When I was taught this, I was always taught put in the the elemental, the dot, the dot multiplier, the dot exponent, or the dot divide, regardless if you're going to use it or not. But I'm not going to do that. I'm just going to leave it out without it here. And then this side here, I'm going to open up two brackets, because I'm going to keep the numerator in one. I'm going to keep the denominator in another. This will be 2 by w squared in the numerator divided by, and I'm going to open up another bracket here for the denominator, rho multiplied. Now I'm going to root v raised power 3, put that in its own bracket, just because I like the exponent to be in its own bracket, especially in a denominator. It's just not so much there. Multiplied by a multiplied by pi multiplied by ar. Okay, so that's the two of them, and I'll just enclose the whole lot of that into one big bracket. All right, so that's there, that function. All right, so what we'll do now is try a plot on that. Plot V against S. No, of course, I haven't done it yet. For I is equal to 1 up to num element. Sorry, everybody, it is late. Num element of V. And I'm going to say S of I is equal to run S function for V of I. Close bracket. And now we'll try a plot of V against S. Turn the grid on. And let's just run that to see we have no errors, and we do actually get a plot, which we do. Very nice. So there's my range up to 500, and I have a minimum happening in here, probably in around the slightly less than 250 mark, in here somewhere. So that looks pretty good. Now we can dress up this plot more. I'm not going to spend an awful lot more time on it, but give me as well. X label is going to be velocity meter per second. And then Y label is indeed f of d over v. which will be my force drag is Newton, so it'll be Newton seconds per meter. Okay. What else could we do in this here? We could put in x ticks, just a x ticks. Let's go from, see, we could probably take this, maybe stay with 100. Let's take it up in 20. Could get a wee bit busy with 25s. Let's try 50, and then let's try it to 400 only. Change that there to 400 as well, and then y ticks. Right, we'll go take that 100, go up in 50s, and then there's probably no need going up much past 400 as well. Alright, so that's because that's, we could probably start that then, say with 125 maybe. Alright, I'll try it there. So yeah, we're in around that 250, maybe slightly to the left of it, but let's keep it there. And we can of course put in a title there as well if you want, but I'll tell you what, let's just move on. Control Alt Enter, let's get a new section in this. So now what I want to do is I want to create a computational space, not for the function itself, but computational space here for running the iterations. Right, so let's go for Alt Enter, and we'll go for computational facilities for say, I don't know what we'll call this, say, tracking down optimum. Want of a much better description, but there you are. Alt Enter. So what we need to have here is we need to have a start and guess. We need to have a place to maybe store our values. You know, each of our velocity values are new velocity values, and yeah, and an error. Of course, we'll run this with a while loop until our error comes down to some set point value. So let's try it. Let's go for I'm going to call, I have my V's S, I'll call S track, and make that equal to V for now. Let's go. So I'm going to say then, actually go for this one. So I'm going to say V initial. Let's go for 250, might be right on it. Let's try 200. It's 200. The first derivative should be tracking me down and to the right. Like in this one here, I could probably even pick 350, 400. I could probably pick 125, and it's always going to track me to this. But we'll check that. So the V initial is going to be that. S track V is going to be that. S track 1 is going to be equal to V initial. So I'm just going to make my first value in S track. It's going to be way too big there. What I'm going to do, I'm going to make, say, n max amount of iterations. So I'm not going to go past 10. S track, let's make it zeros, 1, and then up to n max. So I'm just going to make it a 1 by 10 matrix vector. S track 1 is equal to V initial. Each one of these here is going to have an error. Error is going to be equal to, say, let's call this S track. I'm going to put that one into here. So I don't want error to start off with a V initial value. It won't really matter, but it'll be fine. S track 1, let's go for V initial is 200, n max is equal to 10. So say error, let's go for error 1 is equal to 1. Starting off error. Do it this way. Error current is equal to 1 is equal to error current. All right, then make it 1. Error max allowable, I'm going to make 1 e to the power minus 6, so on, and then I'm going to say n is equal to 0 at the minute. Right, so I'm going to say now while, no, I need to put in my first and second derivatives here. But, so there's my first derivative is up here. First derivative, my second derivative is here. So, all right, so what I'll do is I'm going to just copy this one, and I'm going to use these in, actually write them up top here first. B, so I'm going to say S fun, go for prime. Now, so I'm going to put in a velocity value. It's covered in as V's there, but this is now 1/2 CDO rho, and there's no V in it. And this is minus, not 2, but 6W squared V raised to the power of 4. That's that one. Next is S prime, or S fun D prime, double prime. This whole first term disappears. Second term becomes positive again, and it is now 24W squared rho V to the power of 5. Nice, that's them there. All right, so hopefully that should cover that. Now let's try it. So while error current is greater than or equal to error max, and this is what we're going to run. So while this is greater, we're going to calculate out a new, we go for Alt Enter, I'm going to run Newton's method. This is what we're going to run every single time. So I'm going to say that, and I'm saving this here in S-track. S-track of n plus 1. So what I'll need to do first, I'm going to update my n value in here. Say n is equal to n plus 1. First n is 0, now n is going to be equal to 1, so then I'm going to have 2 is equal to my original S-track of n, which is going to be my initial guess. S-track 1 is going to be 200 minus this ratio here. So I'm going to run my two functions. It's the prime over the second derivative. S prime of take off this here, just getting confusing. My input value to this is going to be in, let's see, s-track v initial is equal to 200. Yeah, it's going to stay on to s-track. This track of n divided by s1 double prime of s track of n. Now that I think yeah, it's all picked up a wee bit of a delay in that, a wee bit of a question I was doing for myself there. That came down to me probably calling it s track as opposed to v track. I really should be tracking velocities, not s itself. You see. So, but however, this is we'll keep it at that. These are going to be looking at my velocity values, because s track 1 is C my S's, they are velocities that are going in. Now, on top of that, I also need to calculate my R, and then because I need to report back at the start of the while loop what my current error is. So my error current is 1 at the minute, which is greater than or equal to max. So my new error current is going to be equal to my error of n plus 1. Well, it's going to be an absolute of my error of n plus error current is going to be the absolute of s track n plus 1 minus s track n. Just do that division first, that difference. Divided up by s track of n plus 1. Okay, that's what my error current is, and then I'm going to say that my error for n plus 1 is equal to error current. Right. Maybe. Let's just get a quick look at this. So why my current, so that is S1 is greater than error max. And now n is going to be equal to 1. So S track 2, my second value in that array is going to be equal to the first one less this adjustment, which is the first derivative of the function at that velocity value divided by the second derivative at that velocity value. And I'm going to write that into that array, the s-track array, the s-track vector. I'm also going to calculate error current. So I need to say error. I'm just going to write the error current here as opposed to writing what that is. So this isn't populating kind of a store of values. I'm just going to calculate a current error. So the current error is currently 1. This one then is going to look at the difference, the s-track n plus 1 value that I just calculated away from the original s-track n value, which will be in this case here 200, the initial being that one, divided by the new value. So that calculates the current, and then I populate my error n plus 1 to that. All right, let's see what happens when we run that. Okay, we have no errors coming out of that, which is good. And what I want to look at here is my s-track. So hopefully we'll have seen that this has converged in on something, which it looks that it has after 6 iterations. The 200 is where I started with 229. I've converged at 2485868. All right, so we could go format long, and we could look at even more digits if we felt that was appropriate, which might just do there. Control Alt Enter. Let's see, just say setup, environment setup. Session and setup. We'll go for clear CLC. Then what we'll also write is format long. All right, let's run it all again and have a look at D or S track. No, not giving me any sort of longer values than that. The format long might have did that. Clearly not. It probably does here out just in the kind of the output space more so than in. And there we can see it in the workspace even itself. Maybe not in these tables. Let's have a wee look at the R there as well. Yeah, so the R's obviously came down, and down here it's obviously less than e to the power minus 6. All right. So we can output our value, or else what we can do is I can just output, say, as track here. Let's run that on it again, and scoot it out here into the longer format. It's taking a little bit of time to come up. Anyway, they're all by 10 to the power 2. So we can see we've converged in here on 248 meters per second, 248.5866.5868. Yeah, so there's 1, 2, 3, 4, 5, 6 decimal places where we're two off at 6 decimal places there, which is 2 millionths. Which is good. All right, so that's our optimal velocity. So we were right. It was just a wee bit to the left of the 250 meter per second value. It's at 248, not a whole lot, nearly 249. But there you are. So that's Newton's method executed. So apologies, it took a wee bit longer than expected. If I had this pre-prepared, I could have went through it probably a lot quicker, but then you lose a little bit of the authenticity of it, and a lot of times whenever you're doing these things, you'll come up with better ways. And like, I didn't comment an awful lot here in places. I started off brilliantly, great intentions, but then these things soon drop off. But you should always comment, of course, writing in. But that's Newton's method executed there. Let me pick up on a more subsequent video now, just from here, and we can use the fact that we have values off of the function here, and it will have the function written, and it's easy call now to run the likes of the golden search method, you know, and our secant line, you know, method as well, just to you know, calculate or define the optimal value in ways that isn't Newton's method. So I'm going to finish it off there at that. So yeah, I hope this has been of some benefit, using Newton's method and using MATLAB to write up a couple of functions and look at plots, and even a little bit there on the for loop. So yes, there's places there where, you know, we could probably get rid of a lot of redundancies, places there we can make the code a little bit slicker. But yeah, here you go. It's just done off the bat, and yeah, it came out fairly well. So thanks very much for joining in, and hope you got a wee bit out of it, and hope to see you in a subsequent video. Thanks very much.